related. We work in all these areas in relation to power converter systems. I am responsible for 3 labs in CIE, which include motor lab, medium voltage lab. We have infrastructure where we can test the power supply up to 6 kilovolt. And then we also have an electrolyzer lab, which is 50 kilowatt electrolyzer installed, and we can change the power supply of this electrolyzer and test the performance of the electrolyzer with various kind of power supply technology. For example, we can have a thyristor-based converter or silicon-based converter or silicon carbide-based converter. And what is the effect of these converters on hydrogen production? That is also one of our research area. In our center, we have more than 10 professors, associate professor and assistant professor as of 2022, but we are growing fast. And recently, according to recent data, we are approximately 40 employees in the center. So, and we started in 2017. So within 7 years, we have grown a lot. Yes. So that was a short introduction about my center. And then I will talk about I hope you can see the new presentation titled Small DC-Link Capacitor Based.
Yes, sir.
Yes, great. So the outline for the presentation will be, I will introduce the system, and then we will talk about rectifier with a small DC-Link capacitor, system model, and negative impedance instability in a small DC-Link capacitor-based system, and then other rectifier topologies. How can we improve the performance by adding extra circuitries? And then we will talk about a typical issue in the 3-level converter with a small DC-Link capacitor. So, 1 second. This is a conventional drive. So we have a front end rectifier. Then we have some energy storage element. Then we have DC to AC inverter, which is feeding the electric machine. If you talk about this system, there are various places you will see inductor and capacitor. This is typically an optional thing. Most of the drives, they do not have this output filter. However, on the DC link side, we have a big energy storage element, and this includes inductor and capacitor. And if you talk about capacitor, the volume can easily go up to 20 to 25% of the whole drive. And the cost can be approximately 10%. And most of the time, we typically we use electrolytic capacitor here. So if we talk about a diode bridge rectifier feeding a capacitive load, then all of us know that there is a the input side current will have the current waveform something like this, right? And the problem with this waveform is high THD, so it can go up to 200%. And then you have a high pollution in the grid. So what we can do, we can try to reduce the DC-Link capacitor and see what happens. So, but what is the value of small DC-Link capacitor? Should it be 1 millifarad? Should it be 500 micro or 10 microfarad? So let's so what should be the value of DC-link capacitor if we want to have a small DC-link? So the limit of the DC-link capacitance value. Now we know that the output voltage waveform will be if we have a large DC-link capacitor, the output voltage waveform will be something like this, a straight line. And whenever there is a charging of the capacitor, so during this time we are charging the capacitor, and after that the capacitor is discharging and supplying the load. And during this time, we do not draw any current from the grid. Okay, and that is the main reason for discontinuous current, something like this. So what we define, or what one can define value of DC-link capacitor in such a way that it tracks the voltage waveform, which is the highest voltage level of the line to line. So we track this voltage. So there is no time the capacitor is not connected to the input voltage. So we don't see this discontinuity. So what should be the value of such capacitance? And you can do a simple calculation and find that this capacitance should be less than 0.0013 divided by the load resistance. Okay, and if we do so, then the output voltage, or the voltage across capacitor, the DC link voltage, will be the 300 hertz, DC voltage with a 300 hertz ripple, and it will directly track the maximum line to line voltage all the time. So if so we did some simulation for that, as so I reduced it to 2 microfarad. One point to be noted in the previous slide, I forgot to mention that this resistance is not constant. It depends upon the load. So if you are feeding a drive from the rectifier system, then the torque can change, and then this resistance will change. So you have to be careful about what should be the capacitance value, and till what point you want to have this 300 the output voltage as a 300 hertz ripple. So I did some simulation for 2 microfarad capacitance. Okay, and then we put constant power load. We'll discuss about why there is a need of constant power load model here. But if we put 2 microfarad capacitor, then you can see we get 3-phase current, which is quasi-square, right? And if we have a quasi-square waveform, then the THD is 32% or 30% approximately, we can say. Now from 200%, we come to 30%. So that is good. So that is one advantage of having a small DC link capacitor, that it can improve the THD for the AC side. Another advantages are that cost is reduced because we have reduced the size of capacitance. If we reduce the size of capacitance, instead of then we can use film capacitor instead of electrolytic capacitor. And if we use film capacitor, then it becomes system becomes more reliable. And then high efficiency. I talk about the system efficiency here because if you have a less harmonic current from the grid side, then you have low losses. So you save some losses. There is a research done, and they can say they claim that up to 8% losses will be reduced if we go for a unity power factor rectifier in the distribution lines. So not in the system, but in the distribution line. So you can save a quite amount of energy. Then I talk about low harmonic distortion. However, there is a disadvantage since we do not have any energy storage element here. Then the system may not perform very well during dynamics. Any change on the grid will directly affect the load side, and any change on the load side will directly reflected on the AC side. So there is no energy buffer in between. So this limits the application of such system to a low performance drives. And then we talk about a system like this. We use approximately 1 microfarad per kilowatt, and it is feeding the electric drive. Okay, but when you have such a system, I mentioned that I will discuss about the constant power load. So when we have such system, the load seen by this rectifier circuit is a constant power load. So when we say about constant power load, it does not mean that I will always draw 5 kilowatt or 1 kilowatt. So power will change depending upon the load, but when certain power or when certain load is applied, then the power is constant. So let's say at this moment we have 1 kilowatt power or 1 kilowatt load. Then the power drawn by this system will be 1 kilowatt. Um, And what is the difference between constant power load and resistive load? A simple way to explain this is, let's say if you have a resistance, the current drawn by the resistance will be proportional to voltage. So if voltage is increasing, current will increase. If voltage is decreasing, current will decrease. But in case of constant power load, since the power is constant and power is product, current is, and if voltage is decreased, current will increase. So you have this. I hope you can hear me. Can you hear me?
Yes, sir. You are audible. Please go on.
Okay. Yeah, there was some change in my microphone, but thank you.
Yes,
So,
sir.
so, so now we have this constant power load, and that is why we have seen a current waveform like this. So you can see it in this. When the voltage is increasing, current is decreasing, and vice versa. Now, what is the problem with constant power load? Okay, so when we have this increase of the voltage and current will decrease, it means we have a kind of negative resistance. Okay, so then there is a problem of negative impedance instability, and that I will talk about in this slide. If we have this negative impedance, what is the system model? And if we talk about the system here, we can simplify the system as a single phase system feeding an RLC load, and the current in this line is always positive. So that will emulate the behavior of diode. And then we have a capacitor here, which is feeding a load, which is right now I have denoted as IDC, but this is a constant power load. So if we have a plain RLC circuit, then we all know the second order system. How what is the capacitor voltage dynamics and what is the inductor current dynamics? We can write this equation. Very standard, no problem about this. And then we will convert this into space state space model. Then you will see it like this, right? So notice here this resistance is in this place with a minus sign. So we have a positive resistance which will come in this state space matrix as a negative quantity. This is very important to note here. And this is something which I would like to stress here. Whenever we are doing a state space model, and I would believe that a lot of you guys will be working on a state space model for RLC based power electronic systems. In our power electronics, we use a lot of inductor, capacitor, and that is not damped. And we know that if we add some resistance, it will be damped. So you have to focus on the element on the diagonal side with a negative sign. And a lot of people might be working on active damping, which I will discuss later, and how we can damp such a system. So the focus should be on this diagonal element. Now we can go ahead and write it in this form: x dot equal to ax plus bu, which is the state space form. No big deal about this. But here you can see the system has two inputs. First is Vin, another is IDC, that is shown here. But IDC is a function of voltage because it's a constant power load. So IDC is nothing but power divided by VDC. So it is a function of VDC. That is shown here, and this makes this system as a non-linear system. So up to this point, since IDC was not expressed as a function of VDC, so we could have treated this system as a linear system. But now in this scenario, it is not a linear system, but a non-linear system, right? And how do we analyze the stability of an operating point of a non-linear system? We will linearize the system around an operating point and then try to find state space equation for the linearized system, and then we try to find the eigenvalue of this guy. So these are the steps we follow for analysis of stability analysis of an operating point of a non-linear system. One more thing I would like to stress here, that when we talk about linear system, then only one operating point is there. So we talk about stability of the linear system. But in non-linear system, we can have various operating points. So we talk about stability of the operating point. So we don't say that non-linear system is stable or unstable. We say operating point is stable or unstable. So now we have to find an operating point and linearize the system with around that operating point. When we do that, then something strange happen. You see a positive value on the diagonal element, and this is a problem. And this is nothing but a negative impedance. So positive resistance comes as a negative here, but negative impedance comes as a positive here. And this may create problem of instability. How? So for that, we have to go for a characteristic equation of a 2 by 2 matrix. So if we talk about characteristic equation, then it will look something like this. Now this is a second order system, and a second order system will be stable if all the coefficients are positive, right? So coefficient of s square, coefficient of s, and coefficient of s raised to power 0. If all three quantities are positive, the second order system will be stable. But here what happens here in this case, this quantity or this coefficient can become negative if this thing is higher than R by L. And when this can happen, if I have a small DC-link capacitor, I have a large power, or I have a large value of inductor. So if I have these three combination, large L, large power, small DC-link capacitor, this is a recipe of disaster in this case. So for stability, it should be positive, but if we go for high power, small DC-link capacitor, and somebody has connected a large inductance on the grid side, then the system can, or the operating point can become unstable. Okay. So how can I stabilize the operating point? There are many ways to do that, and I will talk about two methods: by adding an extra element on the or extra circuit in the system, or by doing something in the control. So when let's say the first thing, if I add some extra circuit on the system. So here we have added a simple boost converter on the DC link capacitor. And if I control this inductor current in a way that current is proportional to DC link voltage. So here I am emulating a positive resistor to nullify the effect of negative impedance. Okay, if we do so, then we can stabilize the operating point. So this is one way. The advantage here, you can see we have a low THD, no output voltage control, high number of semiconductors. So here you increase the number of semiconductor. Another problem here is that the inductor current which we need to control is no more DC, but it's an AC with a 300 hertz ripple. So you need a high bandwidth current control here. Okay. And if you go for high bandwidth current control, then you would like to have a high sampling frequency and high switching frequency and so on. And then this circuit is also associated with certain loss. How? What is the other? What are the other way to stabilize the operating point? Can we do something in this side, on the motor side, to stabilize the operating point? That is what we can see. So we know that the power flowing in the motor is proportional to DC link, proportional to D axis voltage and Q axis, DQ axis voltage and DQ axis current. So voltage and current. So we can emulate a high frequency resistance by changing the power, high frequency component of the power as a function of or in proportion to DC link voltage. It can be done in two ways. One thing is we inject high frequency disturbance on the DQ axis component of the voltage, or we inject the high frequency component of DC link voltage onto DQ axis component of the current. So either of these option can be done. And then if we inject DC link disturbance on the voltage side, then it is added after the current controller. So the current and then the current controller will see this guy as a disturbance. And if the current controller has a high bandwidth, it will try to nullify the effect of this disturbance. So we need a low current controller bandwidth so it does not see the disturbance added here. So that is one thing we have to be careful if we implement this. Or other ways we can add in the current reference, and in that case we need a high current controller, high bandwidth current controller. So it tracks the 300 hertz current ripple added in the reference. So these are the two difference. But and then based on that, this controller should be designed. So these are the two ways we can do. What we have done, we have injected the DC link voltage disturbance in the machine voltage DQ axis component, and then try to model a detailed model and see what should be the value of this gain. So we did this detailed system model. We don't have to go in detail about all these things. Just we know that we have two stator current, two rotor current, one speed, DC link voltage, and the inductor current. So we have a state variable which has 7 variables. So it becomes a large matrix. But the problem here is a positive value of this guy, a diagonal element with a positive value. This is a problem. So how can I make this 0? So to make this 0, what we say that we inject D and Q axis voltage with component of high frequency component of the DC-link voltage. So when we do that, then this term will be, this diagonal term is modified with something like this. So now you see there is a minus sign here. So by changing the value of KD or KQ, I can make this term 0, or I can make it negative. What we try to do here, we try to make this 0, not negative. And we can do it in many ways. So one way is this, another way is this. Okay, and both will result here 0. It will modify something on this side, but we have shown that it does not affect the overall system performance that much. But now we have no positive value on the diagonal element. I am stressing this positive and negative so much because many of you might be working on grid connected converter. And in grid connected converter also you have this LCL or some other filter which can cause oscillation. And in those application also you can focus on, or you can focus on this state space matrix for such system. And if you have instability, and try to see what happens at the diagonal element and how can you make this 0 or negative. So you can relate those things here as well. Now there are some experimental results. So first thing is, when we have a negative impedance instability, you can see we have a high current THD on the grid side, 78%. So we can inject either in D axis or in Q axis. So for D axis voltage and for Q axis voltage injection, we got grid side performance almost similar. However, what happens in the motor current? Because I am injecting a 300 Hertz ripple on the D axis component or Q axis component of the motor voltage. So it will also affect the machine currents. So what happens then? So if I inject in D axis and Q axis, you can see the harmonic distortion on the machine side is worse in case of Q axis injection, Q axis voltage injection. And here when I talk about D axis and Q axis, my D axis is aligned with voltage space vector. So it's not a rotor flux oriented reference frame or something like this. It's a normal V by F control. So if you have to implement this method in rotor flux or stator flux oriented reference frame, take care about this DQ axis conversion properly. But here to implement us in a simple way, we took the D axis as a stator voltage vector. So D axis is aligned with the stator voltage vector. Now, what is the performance of the system in unbalance? So if I have a big DC link capacitor and we have some unbalance in our grid, then sometimes the system can go under single phase operation. So you can see here the grid current is like a single phase. Okay, when we have an unbalance, so one phase does not conduct at all. Only two phases are conducting, so it's like a single phase system, right? But that happens in big DC link capacitance case. What happens in case of a small DC link capacitors? So here I'm showing the performance of a small DC link capacitor drive for unbalanced grid condition with type C 3% unbalance. So you can see the THD is poor, I agree, but it is not going into this, operation where only two of the phases are conducting, one phase is not at all conducting. Okay, and you see this poor THD. This can be improved by the proposed active damping algorithm, which I was discussing earlier. So that was discussed in this reference 16, but here the point is to show the benefit of small DC link capacitors, small DC link capacitor based drive during unbalance. So if you have such case, the stress on the capacitor ripple is also reduced compared to that case when you have a operation where one phase is not at all conducting. Okay, so this is from the small DC link capacitor. If we can do something on the control side of the motor, but can we do something more to have a better performance beyond this? So there are other power converter topologies which uses or which works with a small DC link capacitor and have a better performance. So here I will talk in mostly these two circuits. One is electronic smoothing inductor and second one is current injection circuit based power converter. So if we talk about electronic smoothing inductor, a small circuit is added on the DC link side, and what it does, it tries to control this inductor current as a DC. So if I have a big inductor fed by a rectifier, then it's a constant current load and we draw constant current. So that behavior is emulated by this circuit. So that's why it is called electronic smoothing inductor. And then when you have such inductor current, then the grid current will be quasi square and then you will get 30% THD. This is the best you can achieve in this scenario. Another advantage here is if the load is changing here, since this inductor current is controlled, you will always have a DC current. So you will not have this operation like a big DC link capacitor if load is reduced, even with 5 or 6 microfarad capacitor. So this is an advantage. If load is changing here for very small load, you get very nice 30% quasi square waveform. Okay, but it needs some extra component on the DC link side. Another problem here is the whole DC link current will be processed through this circuit. Although the voltage is small, but the whole current is processed through this. So it's like a series processing circuit. Then we have another kind of circuit, which is like a shunt processing circuit. Here it looks like a VNR rectifier, but it is not VNR rectifier. We'll go in detail of this. We will go in detail about the operation of this circuit soon. So here what we are doing, if we talk about rectifier, let's say phase A, B and C. Phase A has the maximum voltage value, phase B has a middle voltage value, and phase C has a minimum voltage value. So maybe we are talking about point something here. So maybe something like this. So at this moment, phase A maximum, phase B middle, and phase C minimum voltage value. If we talk about, if we talk about that point of time, we know phase A top diode will conduct, phase C bottom diode will conduct, and phase B will not conduct at all at this moment. So the current will be current in phase B will not be there. So what this circuit does, basically it will turn on these two switches S3, S4, which is connected to phase B, and feed this inductor current in this phase. So now I have a possibility to feed certain current in the phase which is not conducting. So what should be the inductor current in that case? the inductor current should be something like this. Okay. So if I have inductor current something like this, then so at that moment maybe current is like this in phase B, or which is the inductor current, then we can achieve a unity power factor in the phase. Okay. So now with this extra small circuitry, we can achieve unity power factor even with passive rectifier. Okay. So this is a good advantage here, but the inductor current waveform is something like this, which is 150 Hertz, which is not DC. So we need to have a high bandwidth current control here as well. And that is why we go for a silicon carbide based system with high switching frequency, high sampling, and high current control bandwidth. So this is one thing, but what about the switching frequency here? Since they have to select the phase with the middle voltage value, so they are switching with the 50 Hertz. So these are low switching frequency devices. So switching losses are not there. Only conduction losses are there. So we can select a proper device for phase selector switch, which does not have high conduction loss. Silicon carbide switches, we go for high switching frequency. So a device with low conduction loss fits very well here. What about inductor? The inductor current stress is very small, because if I have a maximum current of 10 ampere on the grid side, the maximum current on the grid will, the maximum current on the inductor current will be 5 ampere, half of the peak of the phase current. So the energy storage requirement or the size of the inductor will also be very, very small. Okay, so this is a small inductor here. So the size of this extra circuitry can be very, very small. Disadvantage, the disadvantage here is we do not have any DC link voltage control. The output voltage will be same as the rectifier output voltage. Another disadvantage is this topology does not work with big DC link capacitor. You need to have a small DC link capacitor only. And it needs a constant power load. It cannot be, it cannot work with a resistive load. So constant power load, small DC link capacitor, these are the limitation. So it fits very well for our drive application. There are problems here. There may be problems here because I show in the simulation direct, connection to the phase, but it's not the case. You always have an inductor, and when you go from one phase to another phase, while this phase selector switch, you need to take care about this inductor current change on the grid side. Okay, so this is something which needs to be investigated here. How do we do this phase selection, phase transition? Yeah, and then the advantage is unity power factor. Disadvantages I have mentioned. Then I will move on to the last part of my presentation. And since we do not have much time, a 3-level converter fed by a small DC link capacitor on the DC link side. So we all know this is a 3-level converter. When we turn on top 2 devices, we achieve plus VDC. If we turn on these 2 devices, we go for 0. And if we turn on these 2 devices, then we have minus VDC. This is what is shown in this table. So we know this SA and SA3, they will have a complementary switching. SA2 and SA4 will have complementary. So you need 2 independent gate signal for each phase. And we do this by 2 carrier signal. one reference, one carrier will corresponds to top switch, another carrier will corresponds to second switch. And when we do the proper sinusoidal PWM, we achieve something like this. So now you can see here that we have 0 and plus VDC when the reference is positive, and minus VDC and 0 when reference is negative. And whenever you are connecting to this 0 terminal, then you are feeding the load current to the midpoint of the DC link capacitors. And this may cause a problem because point P and N potentials are fixed by the supply or maybe a rectifier on this side. But the point O potential is not fixed and it is dependent upon this I naught current. And this I naught current is the phase current depending upon the switching state. So if we analyze over a fundamental period for sinusoidal PWM, the averaged neutral point current in a switching period will look something like this. So I have shown for 15 ampere output current, 0.9 modulation index and power factor angle of 30 degree. You would see this kind of oscillation, and it's like again 150 hertz amplitude. So you are feeding 150 hertz current to the, or you are drawing 150 hertz current from the midpoint of the capacitor, which will drift or it will cause oscillation of same frequency 150 hertz on the DC link point. If we have output side frequency 10 hertz, then this will be 30 hertz. If we have 20 hertz, it will be 60 hertz and so on. So the ripple is dependent upon the frequency and the amplitude. So it is very difficult for designing a DC link capacitor in such system. And my task was to reduce the size of the DC link capacitor to 7 microfarad. And any disturbance within a switching period in the neutral point current will cause this voltage to drift a lot and the converter will trip. So what we need here, we needed a PWM pulse width modulation strategy which will have zero neutral point current in a switching period. If we can achieve that, then there is the capacitor needs to support only the ripple current in switching frequency range, not in 150 hertz or close to third harmonic of the fundamental. So there is a PWM available where you can have a zero neutral point current in every switching period. So when I say zero neutral point current, I'm talking about averaged in a switching period. So for this, we need to have a modulation strategy, something like this, where when the reference voltage has a middle voltage value somewhere here, when it is close to 0, at that time you need two different carrier signal for top and bottom carriers. Okay. So when we do this, then we can achieve zero neutral point current in a switching period. However, the load can have transient. Load is not always in steady state. So any transient will disturb this reference voltage. It will also disturb the load current. It will also disturb the neutral point current in that manner. And then you can again have a problem of neutral point drift, neutral point voltage drift. So we modified this modulation strategy in a way that we get a very good control. So if we need to control the neutral point voltage, typically what we do, we drift or we shift the whole reference signal by a DC up or down, so we can have some kind of neutral point current control. In this, that will not be good for the plant model, because then for every sector in in a space vector diagram, you need to have a different you will have a different model, and controller design is very difficult. So for that, to get rid of that problem, what we propose that we will not have a DC offset, but we will do some kind of scaling of these reference signal. So we proposed common mode offset, something like this, which is a scaled version. It's not a DC, it's a scaled version of max and minimum signal. And if we do so for various value of K, you can see you will achieve different kind of PWM reference signal. And then, for example, green has more on the positive and less on the negative side. So you can have a different kind of neutral point current for all these values of K. Okay, and when we do so, then we the neutral point neutral point current is directly proportional to the power and inversely proportional to the DC link voltage. Now, if we talk about an operating point, then it is directly proportional to 1 minus 2K. And when we talk about neutral point voltage dynamics, then it comes to be very simple equation, and it is not dependent upon the sector, subsector, nothing. It only depends upon power and the DC link voltage. So a first order continuous equation is obtained. That is the benefit here. And then we designed a controller. You can use a simple PI controller, P controller, whatever, and then design the neutral point voltage control. It looks very difficult to implement, but it is not, because the implementation in microcontroller is also very easy. You don't have to detect various sectors, subsector, nothing. You have to just find maximum and minimum, and subtract minimum from the phase reference, multiply with K, you get the reference for the positive of a phase. You subtract the reference from the maximum, multiply with 1 minus K with a minus sign, then you get the reference signal for the negative carrier signal. That's it. So it is very easy to implement. You need to just sort 3 reference signal max and find max and minimum, and implement this equation in your microcontroller. Very easy. And if we do all those things, then you can see the performance. We have a 300 Hertz ripple, but the DC link voltage is balanced. Again, small DC link. This was the first time we have or anybody has implemented 3-level converter with a small DC link with 7 microfarad, and we have loaded up to 7.5 kilowatt. So this was full 7.5 kilowatt condition. It is easy to design for fixed frequency applications such as grid side converter, but for the motor side, where fundamental frequency is changing, it is very tricky. Then again, we compared with small DC link capacitor, 2-level and 3-level case, and just to show that what is the benefit in EMC results. So 3-level give better performance. Here we can talk about efficiency. Again, 3-level gives better performance in terms of converter and the overall system efficiency. And yes, so last slide, and then we can go for some small question answer. It can improve the system reliability, power density. It may cause negative impedance instability, less energy storage, so dynamics is poor, so it's not suitable for application where you need high dynamic performance. And it needs a robust control because you don't have any energy storage, so you cannot rely on the energy storage big capacitor or something to take care of the disturbances. So you need to be very, very prudent in designing the control. And sometimes it may needs an extra auxiliary circuit to enhance the performance. Yeah, that's the last slide from my side, and then I have some references. But any question from the audience?
Okay. Thank you, Professor, for delivering such a nice and detailed lecture. So, from the audience, if you have any doubt, you can please ask. And I also request the online audience that you may ask questions.
Hello, sir. Am I audible?
Yeah.
Sir, my question is, since you had used, like you were adding the ripple voltage or DCing ripple voltage to the VD and ID, VD or ID
Yeah.
access parameters. So, what is the effect of delay? Has the effect of delay been considered there? Because that will have another negative impedance because of
Effect of, can you say again?
delay, sir. The sampling delay and PWM delays that will be there in the parameters. So the K will instead of R, it will become some kind of a negative impedance.
No, we did not observe that. And since, one second. No, I think I jumped. Sorry. Are you talking about this disturbance, right?
Yes, sir.
Yes. So basically, these are 300 hertz ripple. So, and those delay and all those things are happening in microseconds, right?
Yes, sir.
You are talking about delay time or dead time, correct?
No, sir. Delay time, by delay time, I mean the sampling delay and the PWM delay.
Yes, but that is in, if we talk about sampling delay. So from sensor to the microcontroller, you will have couple of nanoseconds or couple of microsecond delay, right?
Yes,
I
sir.
don't think any controller can take care of that. You have to be you have to have very high bandwidth controller to take care of those effects. So all these things are happening at 300 hertz or something like that. So it should not, I don't think it will be affected by those things. And we haven't seen that in experiments as well.
Okay, sir. Yes, sir. Thank you, sir.
Sir, the parameter which you have made 0 in the matrix. So earlier you told that it should be negative. Then you said that we have made it 0.
Yes,
so
it should not be positive, sorry.
So what is the impact of making it 0 or positive?
So see, if you, yes.
Because it will make the system oscillatory from the characteristic
Yes.
equation.
Yes. So if, let's say, if I have 0 here as well, if I only talk about a simple RLC circuit, if I have 0 here, right? If resistance is not there, if I have a 0 here, then it is what do you call marginally stable LC circuit. It will just keep on oscillating, right?
Yes.
So at least one element should be negative here. Okay, so even if minus R is present and this guy is 0, the system is stable, damped, very good. But in our case, what happens? This guy becomes positive. And this is nullifying the effect of this resistance. So the addition of these two should be negative. And then only you will have a positive coefficient here. Otherwise, you will have a negative coefficient, and then it will make this equation unstable.
Yes.
So what I try to do, I try to make this element 0, and then anyway, I have this resistance which will take care of the damping. But if you want to add extra damping, then you can have something which is more negative here. So it's up to the designer. They can add more. But in our case, if I add more, then it will give more harmonics on the motor side. I forgot to mention one point basically, which I typically tell. So basically what I'm doing here, we are taking some harmonics from the grid side and feeding it to the motor. So now you see the motor has, high THD, 1.66% compared to 1% or something like this. So we are injecting more harmonic on the motor side, so it will create torque ripple and other problems. So I did not make it more negative just to keep it, safe or good for motor. Okay, is that clear?
Yes, sir.
Thank you.
Sir, I have one more question. Since you have a grid connected system with a diode-based rectifier, so the reduction of the DC link capacitance is the effects of non-ideal grid being considered there? Like if the grid is non-ideal or a weak grid, so what effects do they have on the small DC link capacitor?
We haven't considered those things, or haven't analyzed. I'm not in power system, but can you tell me in weak grid you have large inductance or small inductance?
Large inductance, sir.
Large inductance is a big issue here. So if you, and this is what I say here, if you have a large inductance, a small resistance, this quantity becomes small. High power, small capacitance, this quantity become large. It's a problem. And then you are for sure go for instability, unstable operating point, and then you need this. And what I did in my, okay, I did not show basically. No, it is here. So basically what I did in my experiment, I have added some inductor here. So it adds to the grid inductance to show that the system is unstable and how can I stabilize it.
Okay, sir. So is there anything specific that you have done to ensure the stability or only the neutral point current control?
Here I have done neutral point current control, and to ensure instability, what I did here, instead of taking, I did not put that in the slide. What I did, I took the average DC link voltage for the calculation of reference. If you take instantaneous DC link voltage for calculation of reference signal, then it will become unstable. But here I did not do that. So there is another paper which I have written. What you can do, instead of taking the instantaneous DC link voltage, the DC average value of the DC link voltage to calculate the reference signal inside your microcontroller, then you will not have a negative impedance instability, because then we are not going for this this thing. Basically here I mentioned power by VDC, right? So here power is divided by instantaneous value of DC link voltage. But if I take care, if I take the average value of the DC link voltage, then this term is not dependent on the instantaneous value of the DC link voltage. Then system becomes stable inherently.
Okay, sir.
So that's how I have taken care in 3 level.
Sir, what is the performance of those solutions we have told during the transient condition when power is changing from one level to another? So how the system works, means what is the stability of these systems?
If you have a sharp change in the power, this is not a good thing. It is good for pumps, fans, where you do not see a lot of disturbance on the load side. Because as soon as you have a large disturbance, it will affect it will try to draw some power from the capacitor. And then it will, since we do not have any storage on the DC link capacitor, the same thing will go on the grid side, and then system does not behave very good. So not good for sharp change in the load torque. Okay, for pumps, fans, fine.
The speed at which the power is changing or the magnitude of the change in power?
Can you repeat the question?
The speed at which the power is changing or the magnitude of the change in power?
Both, I would say, right? If you say if any speed power is changing, you are changing the torque, right?
Yes.
And in other case, you are changing the speed. So anything will, any disturbance or any sharp change will cause some issue on the grid side or the small DC link capacitor on the DC side or the AC side. It will directly reflect there, right? And this guy does not have any kind of energy storage to support those disturbances. So not good. What I did in our lab, I had a DC motor coupled, and then I changed the resistance load on the DC link motor. Sorry, DC motor. Now, if I change the resistance on the DC motor has its own dynamics, so it will take some time to convert that into the speed and torque, and then it was a slow process. With that, it works. That's what I did in the lab. But not like a sharp change in the torque, or even if I have a sharp change in the speed reference, speed was ramped down.
Okay.
Okay. So at the end, I would just again thank you, Professor Ramkrishan Maheshwari, for accepting our invitation and delivering such a great lecture. And I would like to thank our faculty advisor, Dr. Ravindra Thadda, for encouraging us to organize such a great event, such a nice event. And I would also like to thank the audience and the volunteers to organize such an event. And before we just end the meeting, I would like to just have a group photo. So please, all of you come on the dais.
Just pin it.